Welcome back. Last lecture, we began our exploration of the science of engineering mechanics, the study of forces acting on bodies. And to guide that exploration, we developed this roadmap, a diagram that shows the major concepts used in structural analysis. Last lecture, we focused on the first block of this diagram, external forces. And we saw how two types of external forces, loads and reactions, are related by the all-important principle of equilibrium. Along the way, we met two men who pioneered the principle of equilibrium. Isaac Newton, who formalized the principle in his first law of motion in 1687, and Newton's predecessor, Simon Stellan, that really unique Renaissance-era mathematician who developed the world's first proof of equilibrium using this ingenious thought experiment, consisting of a string of beads draped over an inclined plane. Stellan was evidently quite pleased with this insight because in his book, underneath the diagram, he wrote, "What seems mysterious can be understood," a phrase he later adopted as his personal motto. Well, in the spirit of Simon Stellan, let's focus this lecture on understanding the remaining major concepts of structural analysis on the roadmap: internal force, stress, and strength. During this lecture, we'll see that loads, which are external to the structure, cause internal forces to develop within the structural elements that compose the structure. And we'll see that these external and internal forces have to be in equilibrium with each other. We'll see how internal force is manifested as stress, a measure of the intensity of that internal force. And we'll also learn once again about strength, the characteristic value of stress at which a particular material fails. And we'll see where strength comes from, how it's determined experimentally in the lab. And then finally, we'll compare stress with strength to evaluate structural performance. These concepts in total describe how structures carry load. And so they'll lie at the very heart of our analysis of the world's great structures through the remainder of this course. When all is said and done, I hope that Simon Stellan's motto, "What seems mysterious can be understood," will ring true for you as well. Now, there's a good reason why all this mysterious stuff can be understood. Much of what we know about the strength of engineering material is gleaned from a very simple laboratory test that scientists and engineers have been using for centuries. Today we call this the simple tension test. And it's done by simply taking a specimen of material, mounting it in a testing machine, and then using that machine to slowly pull on the specimen and stretch it in tension until it breaks in two pieces. That's it. If you can understand this test and the information we glean from it, then you'll understand the concepts of internal force, stress, and strength, the subjects of today's lecture. Oh, and by the way, the test specimen that I just used for our simulated simple tension test is, in effect, a structural element that's subjected to pure tension. In other words, it is one of our 6 basic types of structural elements. So, by the end of today's lecture, you won't just understand these key concepts from our roadmap, you'll also understand how tension members work in great structures. Great structures like the Sunshine Skyway Bridge across the Tampa Bay in Florida, shown here. The structure is called a cable-stayed bridge, and the cable stays are all tension members, which radiate out from the two towers in a way that's intended to evoke the appearance of a sailboat. Clearly, the designer of this bridge wanted us to appreciate these tension members because he had them painted yellow just to make them a little bit more prominent. So let's begin our exploration of tension members by looking at the historical development of that all-important laboratory experiment, the simple tension test, that tells us so very much about key structural analysis concepts. In doing so, we'll see some of the seminal discoveries that really ultimately helped foster the era of science-based design. During the Renaissance, Leonardo da Vinci performed a number of very well-conceived mechanics experiments and then recorded them in his notebooks, so we know about them. One of those sketches, which I've replicated here, is entitled "Testing the Strength of Iron Wires of Various Lengths." The setup for this test, as Da Vinci depicted it, consisted of an iron wire, which is the test specimen, attached to a support at the upper end, which you can see here in this diagram, and has a bucket hanging from the lower end. To do the experiment then, Leonardo hung a bin filled with sand above the bucket. He opened a hole in that bin and allowed sand to pour out into the bucket gradually until the wire broke. He then weighed the bucket to determine the force at which the wire had broken. This is a measure of the strength of the wire. Now, as one of the earliest systematic experiments on materials, Leonardo's tension test was a noteworthy effort. But as science, it was mostly unsuccessful because Leonardo erroneously concluded from his experimental data that the strength of iron wire depends on its length. In fact, what we know today is that the strength of any tension member is actually independent of its length, a fact that ultimately was proved by our next great pioneer of engineering mechanics, Galileo Galilei. Galileo published the world's first comprehensive scientific study of the mechanics of materials in 1638. And in an interesting, indirect way, we actually owe this publication to the Catholic Church. 6 years earlier, Galileo had defied the Church by publishing his assertion that the Copernican theory of planetary motion was indisputable truth. As a result, he was called to Rome, he was condemned, ultimately placed under house arrest in his villa in Tuscany for the remaining 8 years of his life. Throughout this final period, these final 8 years, Galileo focused his work primarily on mechanics, probably because the subject was likely to be significantly less controversial than cosmology. As a result, his great work was published during this period. It was titled Two New Sciences and really was his seminal treatise on engineering mechanics. Galileo's experiments established the fact that the strength of a structural element is independent of its length, and thereby he disproved Da Vinci's earlier experimental results. But more importantly, Galileo showed convincingly that the strength of a member in tension depends on that member's cross-sectional area. Okay, so what's a cross-section and what's cross-sectional area? Well, the cross-section of a structural member is really just the two-dimensional shape that's formed by cutting through the member on a plane perpendicular to its long or longitudinal axis. So if this were a concrete member, it's cylindrical in shape, the long or longitudinal axis of the member is running this direction, and when I make a cut, I expose this shape, it's a circle, and that circular two-dimensional shape is the cross-section. The cross-sectional area then is simply the area of that circle, pi r squared. Many other types of configurations of structural members are possible, and you've seen them in the world all around you. This is a standard 2x4 piece of lumber that's used often in construction, and it has a rectangular cross-section. In fact, the very definition of the member, the 2x4, describes the dimensions of that rectangular cross-section. In steel, we often see structural elements made with an I-shaped cross-section. Now, this is really just a short segment of member. In practice, the real steel beam probably runs about 20 or 30 feet in this direction. For our purposes here, we're really just concerned with the cross-section itself, which forms an I shape, as you see here. And later on, we'll talk in more detail about I-shaped sections, but for now, recognize that it's composed of three elements. The top and bottom horizontal planes we call flanges. The vertical plane we call a web. And steel cross-sections are also available and often used in hollow tube configurations. This one happens to be square, but we also often see hollow tubes that are rectangular or circular in geometry. Okay, so back to Galileo. Now, based on his experiments, Galileo discovered that the strength of a member is directly proportional to its cross-sectional area. For example, a member with a cross-sectional area of 10 square inches is twice as strong as a member with a cross-sectional area of 5 square inches, as long as they're made of the same material. This discovery eventually led to the development of the concept of stress. But it took a long time, almost 200 years, for engineers and scientists to ultimately get to that conceptual understanding. In the meantime, around 1650, an English scientist named Robert Hooke also performed an extensive series of tests on iron wire. These were similar to Leonardo's and Galileo's experiments in that a piece of iron wire was subjected to tensile loading, But Hooke went a crucial step farther. Rather than simply determining the breaking point of the wire, he also investigated how it elongated under the full range of load, from 0 all the way up to the breaking point. Let's simulate Hooke's experiment here, just to give you a physical sense of what he did. Instead of iron wire for this demonstration, I'm using this piece of rubber tubing, just so it'll be a little bit easier for you to see. To run his test, Hooke suspended a piece of iron wire from a frame, and then he hung a pan from the bottom of that wire. Okay? Once the pan was in place, he recorded its position using some sort of a measuring device like this, and then instead of applying a steady stream of sand to load the member as Da Vinci did, he applied the load in a series of increments using known weights. So he took a known weight, let's say it's equal to 1 pound, he laid it in the pan, and he measured the amount of deformation, the amount of elongation of the specimen that occurred as a result of that known discrete load. He recorded that data, the load and the amount of deformation. Then he added another known weight, watched the deformation. Once it stabilized, he recorded the amount of displacement, that is, how much the member elongated as a result of that additional increment of load, and he continued to repeat that process, each time recording load and deformation until the specimen finally broke. At this point, he plotted the data, load versus deformation, and when he plotted the data, an amazing result emerged. As you can see here, the experimental values of load and deformation plotted as a near-perfect straight line on a graph, almost all the way up to the point of fracture. Hooke probably made this discovery sometime in the 1650s, but he didn't actually publish it until 1678 because the discovery actually gave him the capability to build very accurate clock springs, and he didn't want to give away his competitive advantage. When he did publish the discovery, he used a simple Latin phrase, ut tensio sic vis, as the extension, so the force. The discovery of this linear relationship between load and deformation is so important to modern engineering mechanics that even today we call it Hooke's law. Groundbreaking as it was, Hooke's discovery was fundamentally limited by the fact that he only ever considered the external forces acting on the test specimen. He never actually made the conceptual leap from external force to internal force and then stress. To see what Hooke overlooked, let's return to our tension experiment and draw a free body diagram of the test setup. First, we isolate the member, the simple tension member. We then add the load down at the bottom, 4 pounds oriented in the vertical direction, downward. Up above, we'll add the reaction that keeps the body in equilibrium. We'll label that R. And since the body is in equilibrium, we know that because it's not moving, then all the forces acting on it must be in balance. Clearly then, the magnitude of that reaction has to be 4 pounds. We have 4 pounds up and 4 pounds down. This configuration, by the way, is often called axial loading because both the load and its reaction are aligned with the long, or in this case, the longitudinal axis of the member. But both the load and the reaction are external forces, and what we're interested in understanding is what's happening inside the member. To do this, we have to do another thought experiment. What we're going to do is imagine cutting completely through the member to expose that internal force. And then we'll use the principle of equilibrium to figure out what that force actually is. Let's use our free body diagram as a way to see how this process works. Here's the free body diagram, once again, of our tension test specimen. And now here's the location of the cut. It's just a conceptual cut, but it's used as a problem-solving tool. Now we can isolate the portion of the member that falls below the cut and draw a separate free body diagram just of that segment. The 4-pound load is still applied on the end of the segment, and so the only way that this segment can possibly be in equilibrium is if there's some additional force acting up there on the face of the cut. We know this little segment is in equilibrium because it's not moving, and therefore there is a force on the face of that cut, and that is the internal tension force, which you can see here. Clearly, the principle of equilibrium tells us that this internal force, F, must be exactly equal to the external load, 4 pounds. Okay? Now, at first glance, this analysis might seem trivial. We applied a 4-pound external load, and it resulted in a 4-pound internal tension force. What's the difference? Well, there is a difference. it's very important to recognize that the external load and the internal force are two very different things. In the simple tension test, they happen to be equal. But in many other situations, they won't be equal. For example, if I just reconfigure this experimental setup, that is, if I take the load off for a moment, and rather than having the load suspended from a single wire in one uniaxial test setup, suppose the load is suspended from two wires, which are oriented such that they form an angle. Now, in this circumstance, there is not one internal force, but two different internal forces, and both of them will turn out to be substantially different from the externally applied load. More importantly, the external load and the internal force are fundamentally different phenomena. The external load is a concentrated force that's transmitted to the member or members through some sort of physical connection to another object. In this case, the connection is the pan holding that 4-pound weight. The internal force, on the other hand, is an attraction between the molecules that constitute this material. It is internal. When we apply a load to a structural element, it stretches slightly. And as a result, the individual molecules that make up the material have to move away from each other ever so slightly. The chemical bonds between these molecules are very strong, and they resist being deformed. This resistance, accumulated over the entire cross-section of our conceptual cut, is the internal force that keeps the lower portion of this member, as you see it in our free body diagram, in equilibrium. Now, this idea of internal force as an accumulation of molecular level resistance to deformation is a really powerful concept that actually leads us directly to the concept of stress. This concept was vaguely suggested, indirectly, by Galileo's experiments of 1638. But it wasn't until 1822 that the French mathematician Augustin Cauchy actually formulated the concept of stress as we know it today. Stress is the intensity of internal force in a member. And in an axially loaded member, it's calculated simply as the internal force divided by the cross-sectional area and expressed in units of force per area. For example, pounds per square inch, newtons per square meter. Stress is independent of geometry and material type. For example, if a long steel bar with a cross-sectional area of 2 square inches, as you see here, is loaded with a tensile force of 2,000 pounds, then the stress in the bar is 1,000 psi, 2,000 divided by 2. Now, if a short concrete cylinder that has a cross-sectional area of 10 square inches is loaded with a tensile force of 10,000 pounds, well, the stress is still exactly the same. It's 1,000 psi. In this case, 10,000 divided by 10. The concept of stress is so powerful because the strength of a material is defined in terms of stress. For example, the strength of standard grade structural steel is about 36,000 pounds per square inch. Doesn't matter if the piece of steel is long or short, wide or narrow, circular or eye-shaped, the material will fail when the stress reaches 36,000 psi. Okay, that's stress. Next, Augustin Cauchy's second contribution to today's lecture is the associated concept of strain. Just as stress is the intensity of internal force, strain is the intensity of deformation. As we saw in Robert Hooke's experiments, a member loaded in tension elongates. Strain is a way of characterizing this elongation in a particularly useful way. Now, beware that in everyday usage, the words stress and strain tend to be thrown around in a very imprecise way and often are used more or less synonymously. In engineering, these are distinctly different concepts, and you have to use the terms very precisely. Stress is a measure of internal force. Strain is a measure of how much the member deforms under load. To calculate strain in a tension member, we simply divide the amount of deformation by the original length of that member. For example, if the member is originally 100 inches long and it deforms 2 inches under load, then the strain is just 2 divided by 100, or 0.02. Now notice that strain has no units. In the calculation, inches are divided by inches, so the units cancel out. You can think of strain as if it's a percentage. In this example, a strain of 0.02 actually means that the member has stretched 2% beyond its original length. So it's really not a complex concept. Now that we have a basic understanding of both stress and strain, let's put these concepts to work. Following the example of Leonardo, Galileo, and Robert Hooke, let's go to the laboratory and do a simple tension test. We'll run essentially the same test as Robert Hooke did back in the 1650s, but with two important differences. First, we're going to use a much more sophisticated piece of testing equipment. This large hydraulic testing machine that's capable of applying tens of thousands of pounds of load to a test specimen. So we'll be able to test much larger specimens rather than just thin wires. The machine also has a built-in measuring device that automatically records load and deformation of the specimen very accurately, so we don't have to do the manual measurements that we saw in my earlier simulation. Second, rather than plotting our results in terms of load and deformation as Robert Hooke did, we're going to plot our results in terms of stress and strain. Now remember, the conversion is quite simple. To plot stress, all we do is take the measured value of load and divide it by the cross-sectional area. To plot strain, we take the measured deformation and divide it by the length of the original specimen. The result of this test is a graph of stress versus strain, which is commonly called the stress-strain curve. And here we see a typical example of a stress-strain curve for structural steel straight out of the laboratory. The stress-strain curve is an extraordinarily powerful tool because it characterizes not just the specimen that we tested, but the material that that specimen was made of. In other words, if I test 10 different specimens of different shapes and sizes that are all made of the same type of steel, then the stress-strain curves for all 10 of those tests will look exactly the same, just like this one. And the stress-strain curve tells us almost everything we need to know about a material's mechanical properties and about its suitability for a particular structural task. Think of the stress-strain curve as the fingerprint of an engineering material, and you're pretty well along the way to understanding why it's so valuable to us. Let's examine this particular stress-strain curve for steel a bit more closely. We're going to read this graph like a book from left to right. So the curve begins, logically enough, down at the lower left-hand corner, the point where we have zero stress and zero strain. Makes sense. At the start of the test, there's no load, and the specimen hasn't undergone any deformation. So both stress and strain should be zero before we begin to apply any load. Now let's switch on that big hydraulic testing machine and slowly increase the load, which corresponds to increasing values of stress, load over area. At the same time, the specimen is beginning to stretch, to elongate, which means that there's a corresponding increase in strain. Hey, and guess what? Just as Robert Hooke predicted, the relationship between stress and strain is almost perfectly linear, up to a stress of about 50,000 psi. This linear region of the stress-strain curve has a particularly important characteristic. If we load that specimen, say, up to 40,000 psi, so it's still within that linear range, and then we remove the load entirely, the specimen will then return all the way back to its original length with no permanent deformation at all. We call this elastic behavior. And just to illustrate the point, if we come back to my simple tension test specimen and we remove the load, you'll notice that the specimen does in fact return all the way back to its original length. There's no permanent deformation. This is elastic behavior. Now, continuing our tracing of the path of the stress-strain curve, as the load increases beyond this point, at a stress up around 55,000 psi, something very interesting happens. The stress-strain curve abruptly peaks, then it drops off a bit, and then it becomes horizontal, meaning that large strains are occurring with no increase in stress at all. The material is actually stretching like taffy. This behavior is called yielding, and it means that the metal is beginning to fail. Its crystal structure is actually starting to break down. The key characteristic of yielding is that it involves permanent deformations. Now, if the load's removed, the specimen won't return to its original length. But you know all about yielding. It happens to you all the time. When you go into your closet and you've run out of hangers and there's only one left and you hang 3 suits on the hangers, this happens. And when the hanger bends beyond the point when it springs naturally back to its original shape, what you have done is to cause the material to yield. And as you see, the deformations that occurred as a result are permanent. They didn't come back out after the load was removed. We call this plastic behavior. Beyond that region of yielding on our stress-strain curve, the curve now begins to rise a bit, though at a much shallower slope than the elastic region of the curve. Eventually, the curve peaks, it drops off, and then the specimen finally fractures. That means that it physically breaks into two pieces, just like that earlier simulation I did. Now, note that the value of strain at the point of fracture for structural steel is over 0.25. Think about what that means. That means the steel has elongated more than 25% beyond its original length before it finally failed. It's a very important quality of steel that we'll talk more about later. The stress-strain curve that's shown here on this graph is actually quite typical for structural steel, but the curves of other materials can be vastly different. For example, this is a typical stress-strain curve for cast iron. Notice that it doesn't have that distinctive horizontal yield region, and the strain at failure turns out to be much, much, much lower than it was for steel. You have changed the size of the horizontal axis of the graph. Remember that the maximum strain for steel at failure was up close to 0.3. For cast iron, is somewhere in the neighborhood of 0.003. That's 100 times smaller. Remember, the stress-strain curve is the fingerprint of the material. The differences between these two fingerprints tell us a tremendous amount about how these materials work in structural applications. They're going to allow us to distinguish between the important mechanical properties for the purpose of design. The three most important properties of an engineering material actually can be read directly from the stress-strain curve, no matter what its shape is. Here again is our typical stress-strain curve for steel. And the first of those critical qualities we want to evaluate is the height of the stress-strain curve, shown here. And that height corresponds to the largest stress that the material can endure before it finally fractures. This stress is called the ultimate strength of the material, and it's measured in units of stress, since it's measured vertically on this graph, such as PSI, pounds per square inch. Second important material property is represented by the width of the curve, and it corresponds to the material's capacity to undergo large, permanent plastic deformations before it finally fails. This capacity is called ductility. We'll talk a lot more about it next lecture. And finally, the third property is represented by the slope of the lower elastic portion of the stress-strain curve. It's a measure of the resistance of the material to elastic or non-permanent deformation. This property is called stiffness. We're going to revisit these ideas of ductility and stiffness in more detail next lecture. For today, I just want to focus on strength, which is by far the most important of the three material properties. As our roadmap reminds us, the strength is the principal basis for evaluating the performance of a structural element. When the actual stress in an element is greater than the strength, then the material will fail. When the stress is less than the strength, the material won't fail. Engineers use this fundamental evaluation as the basis for designing structures. That is, determining the size and shape of each individual member in the structure to ensure that the stress is always less than strength, no matter what the externally applied loads are. Now our exploration of the structural analysis roadmap is complete, and I hope that Simon Stevin's motto has proved to be true for you as well. What seems mysterious can be understood. Remember that in every one of the experimental tests that we've just looked at, the test specimen was a tension member. It was axially loaded in tension with a tendency to elongate. So our exploration of the concepts of internal force, stress, and strength has also taught us everything we actually need to know about the first of our 6 basic structural element types. Tension members are all around us. They hold up the chandelier in my dining room and the swing in my backyard. My dog's leash is a tension member. And as the rope in this particularly vicious-looking tug-of-war indicates, it's also represented by that rope. But most importantly, we find many tension members in great structures. For example, here's the beautiful Golden Gate Bridge. And if we look closely at the bridge, we'll see these vertical cables, the suspenders that I referred to back in Lecture 1, are excellent examples of tension members. They're called suspenders because they suspend the bridge deck from the main cable, so they're clearly loaded in tension. The Golden Gate Bridge has 500 such suspenders, arranged in bundles of 4, as you see, and spaced at 50-foot intervals along the entire length of the bridge. The suspenders look tiny in this photo, but in fact, each one is a bit over 2.5 inches in diameter and can carry about 500,000 pounds of internal force. Note that these members behave just like specimens in a simple tension test, except that they've been designed such that their actual stress always remains well within the elastic range of material behavior. In this lecture, we've looked at 2 great structures. Up front, we saw the Sunshine Skyway Bridge, and here we see the Golden Gate Bridge. You might have noticed that both of these examples are relatively modern, dating from the 20th century. This is no coincidence. Our main construction materials available today have significant strength and tension, but the materials available to earlier engineers, stone, brick, concrete, and wood, were much more limited in their application. Of those 4, only wood is capable of carrying significant tension forces. Later in this course, we'll see some tension members in early wooden bridges and roof trusses, but in general, the extensive use of tension members in structures only became viable with the advent of mass-produced wrought iron in the 18th century. We'll learn much more about this development next lecture as we apply our newfound knowledge of basic mechanics to explore the wonderful world of materials. And when we'll see how the choice of materials contributes to just about everything we see around us in the built environment. Until then, thank you.